going to sort of start catching up to you guys. It's kind of nice to have 3 locations where these things meet, right? So I have 3 points where these guys meet. That's pretty good. And then I could just draw the shape on top of that. So I've got, we draw this guy. He's the easier one to draw. Side of that. So we go with that first piece. Hopefully. If I want you to find where 2 functions intersect, you just set them equal to each other. That makes physical sense. So at 0, the line is at 1. At -1, the line is at 0. And at 1, the line is at 2. So there's the line. That'd be awesome if I had a straight edge. Let's see what I can do here. Woohoo! And now, this guy is not horrible to graph. It's just x cubed lifted up by 1. Right? So if you wanted to, so it meets here. So I know it's here. And what's a cubic do? A cubic does this kind of thing, right? So it's going to do that same thing, but now it's going to go through here instead of the origin. So it's going to go up and over, and then it's going to go here. Wah! Is that perfect? No. That's fine. I'm showing the points of intersection. I got the shape, and I've got the important thing. For example, below 0, which function is on top? Below 0, which function is on top? X cubed plus 1. You guys just don't like to talk to me. That's okay. X cubed plus 1's on top. And over here, the line's on top. That's become very important on that last thing I asked you to do. So pretty cool with that so far. I mean, this idea of being able to sketch rough sketches, but they show the important parts. And of course, part of what we're getting into is what are the important parts going to be? What would this represent? What does that represent? What does the integral x plus 1 from 0 to 1 represent? Yeah, and let's be a little more specific like I did last time. It's not just under, it actually stops where? It's the area between the function and x-axis. Kick-ass. Is that cool? Right? So that would be on the picture, that would be this area all the way down, right? Okay, that's what we learned before. And of course, what would this represent? Same idea, but from x cubed plus 1 down. Notice I'm only talking from 0 to 1, just so I only have this one area to look at. Make this little banana area here. Because what do I end up with? What does this represent then? Now that you've got those two ideas on there, the difference would represent the area where? This difference would represent what area here? If x plus 1 is from there down and x squared plus 1 is from there down, so the difference would represent the area where? Yeah, shade the banana. Ah, that area. So 6.1, the title of section 6.1 is area between curves. So if I want the area between f of x and g of x, I'm going to take the difference between them and look at it. So here's another way to look at this. Okay, so everything I'm doing is getting this ready for when things get a little bit more complicated. This one is relatively straightforward. If I subtract two areas, I get the area between. That kind of makes sense, just by itself. But let me say this. If I want this area right there, as x goes from 0 to 1, what is y doing? As x goes from 0 to 1, that's what this piece says, right? Go from 0 to 1. What is y going between? So as x goes from 0 to 1, y is going from here to there. So when we built up the idea of area, what did we do? I'm just going to borrow this guy. We had a function y, and we put in little rectangles. Whee! And where were the rectangles between? They were between the function and the floor. Now, of course, what is this? This is 0. So what was the height always? F of xi, whatever the hell that was right there, right? Is that cool? That was what the height was. But now if I want the area between two curves, what's the floor going to be? What's the height of that rectangle right there? What's the height of that guy? How tall is he? How tall is that rectangle right there? How tall is he? Bless you. Yeah, f of x minus g of x at that point, whatever that point is. You guys with me? So if you read the book, which you haven't tried it, you should try it. You could do the whole damn rectangle shit all over, and that's sort of what they do. At this point, that's kind of silly, because we could tell already how to get the area in this region just by the idea of integral that we've already developed. It's just going to be the whole integral below this guy minus the whole integral below this guy. Of course it's going to leave me with that little banana shape. Does that make physical sense? Please, dear God, let that make physical sense, right? If this is 7 and this is 5, then this is 2. I mean, that's all it is. I like it. I like it. Almost too nice to believe. So if you look in the book, and they make Riemann sums, but they build their rectangles between the two functions, so the height would be f of xi minus g of xi. And if you do the whole Riemann sum thing, I don't know if you have any word in it, but when you do the rectangle thing, if you do the whole thing with that in it, of course you're going to end up with the integral of f minus g, because that's the function you're dealing with now. So the shortcut for finding the area between two curves is going to be find where they meet and then integrate the difference between the two. What's really important there is who's on top in that region. That's the one that's got to come first, right? Maybe. This kind of integral will always come out positive because it is a true physical area. So go ahead. I don't know if you guys have done this yet. Have you guys done this integral yet? That'd be good. Review. These functions are kind of really, really nice. The ones cancel, you end up with x minus x cubed in there. What's that integral? What do you get for the antiderivative? I forgot you guys like to keep secrets. Okay. X squared over 2 minus x to the 4th over 4. It's a polynomial with no constant pieces, which is really nice. You've got to be careful, though. I'm trying to tell you about a trap you could fall into. This side is going to be 0. I can forget about it. But the minute I have like e to the x or natural log of x plus 3 or something, that's not going to get zeros. People kind of fall into the trap of not even putting 0 in, ever. And then here it's going to be 0, yeah. You don't have to worry about it. But that's because it's polynomial. No constant piece. So it's only going to depend on what 1 is. So 1 is going to be 1/2 minus 1/4, which is 1/4. Okay. All right. It's not too bad. So as long as you get the right function first, the one that's on top, minus the one below, that's going to always come out to be the actual physical positive area between those two functions. So if I would have said from -1 to 0, I want to find the area in this banana from -1 to 0, what would have been the differences? This would have been from -1 to 0, and what would it look like on the inside? Find the area between those two. Yeah, what's first? What's on top? What's happening? Which function's on top between -1 and 0? X cubed plus 1, yeah. So the top function minus the bottom function. And then you would have went through all the steps, blah, 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 blah. I like it. What do you guys think? Because of the symmetries involved, obviously, what do you guys think about the areas of those bananas? They should be the same. They should be equal, yeah. In this problem, be really careful. We are going to use symmetry sometimes to make problems quicker, but you can't always tell if the symmetry is right, especially if anybody has to take Calc 3. That's a really big trap to fall into. But we will use symmetry sometimes to make things quicker. All right, now, let me transition up to the board. I really don't like using the overhead, but oh well. All right, little camera, you're drunk. Okay, so that's one idea, right? What also happens in this section is kind of a nifty idea. We are way too used to everything being determined by x, which is not like something you should have any control over, really, because that's sort of the way we've been working with things. But kind of like, let's do this example. What was it? I had developed a nice little example. Yeah, just that. So if I say y equals x squared, and I want to find the area from under x squared, between x squared and y equals 0, from x equals 0 to x equals 2. All right. Take a second and sketch that region out for me. What's that region look like? y equals 0, what is that another name for? Y equals 0? What's that another name for? Where is y equals 0? Somebody give me a point where y is 0. Just any point where y is 0. 0, 0, Jeff. Okay. Good job, young Jeff, man. Give me another point where y is 0. Any other point where y is 0? No, it's not points. 1, 0, 2, 0. So what does y equals 0 mean? The x-axis. Y equals 0 is the x-axis equation. So what's the equation of the y-axis? X equals 0. It's crazy. Why are those the equations? Because that's what's true on those lines. Okay, I like it. I like it. So be really careful. You don't see enough of that. And then all of a sudden in this chapter, this is going to happen a lot. Y equals 0 is another name for the x-axis. X equals 0 is another name for the y-axis. You should remember that y equals constants are this way. X equals constants are this way. Okay, I like it. So this is a very simple graph. Simple little graph. Between y equals x squared, that's one wall. One wall is y equals x squared. Oh, from x equals 0 to x equals 2, so this is another wall right there, x equals 2. And then this is the last wall. So that's the region that's described by that. Are you guys cool with that? Okay. So this is a very simple integral. Find that area real quick for me. So this is an old idea, but I'm using a slightly different way to describe it. Make sure everybody's setting this up correctly. What would this integral look like from 0 to 2? And that's what x is doing, right? Here's something really important to get used to. Now that we have the basic idea of what this symbol means, we're going to get more technical about how to interpret it because we're going to start to do more and more with it. So we haven't had to say what I'm about to say before. 0 to 2 is what x does, and I sort of kind of hinted at that before. That's what x does. X is going from 0 to 2. Y is going from 0 to this. That's why the inside actually technically would be this. Because what's y going from 0 to x squared? But of course that minus 0 doesn't show up, right? So you would just write this. So if I integrate a function, it's understood to be between 0 and that function because I would have like a minus 0 on it. If I wanted it to have a different floor, I'd have to minus the equation of that other floor. So before now, it was not as complicated because we were just considering the x-axis to be the floor, but now we're realizing, oh, the floor could be different things. Maybe. You guys all right? You guys all right? No? A little bit? All right. Okay. So yeah, I know, we never wrote it like this because we really didn't have to. I just wanted to get the idea of integral down. So now we can be a little more general about what we're doing. Now this is a simple integral. What do you guys get? Yeah, and again, this is where 0 won't contribute anything. Right? So I just get 8/3. I like it. All right, so I came up with this example, and there's a lot of different ways I can kind of attack this, but let me show you this. How would I describe this region here? What if I wanted that area? There's two ways to get it now. Does anyone see a way? I call this a cookie cutter problem. I have cut the funkiest looking cookie out of this sheet of dough. How big is the sheet of dough? The whole thing is what? What's the whole area? The whole area of this whole thing. 8. Does everybody see that? It's just a rectangle, big ass rectangle. And how much are we going to chop out to get this red piece that's left? Look at this funky ass looking cookie cutter. Schwamp. All right, that's the sound it makes. How would I figure out the red area? Well, I know what the blue area is. 8/3. Now watch. Real silly little shortcut. I know, I don't care. What's a whole 8 minus 1/3 of an 8? 2/3 of an 8. 16/3. That kind of thing happens a lot, so it's a really cool little shortcut to get. It's not like this is hard to get LCD or bullshit, but it's nice to know. Or not. And some of you guys are like, I got this thing, Jeff. You ever heard of the calculator? Ah, damn it. A whole 8 minus 1/3 of an 8 is 2/3 of an 8, which is 16/3. That's a beautiful idea. If you don't think so, that's fine. Now. So there was one way to get that area right there, because we already did this interval. I already knew what this area was. I know what the whole area is, so I can just subtract. Any other way that I propose to get that red area better freaking come out to be 16/3, or else I got to throw that shit out. And this is anytime, all right, anytime that we discuss a brand new idea, the example I'm going to use is going to be a really simple example, just to get the idea now. So what we're about to do is completely unnecessary for this problem, because we already know the freaking answer. But it will be completely necessary for more complicated problems coming up. Okay, so I don't want your brain just to go, shit, why is he doing all this weird shit? Because this is an easy example to step into this idea. Okay, so watch. What's kind of, so to describe this region, I can say the blue region, let me do this in blue, that'll make more sense. The blue region, as x goes from 0 to 2, y goes from 0 to x squared. So that's what I said earlier, but I want to really write that all out. As x goes from 0 to 2, so pick an x in between 0 and 2, like this x. What is y going from 0 to this, which is x squared? So as I let x move along 0 to 2, if it's right here, that y goes from 0 to x squared. That y goes from 0 to x squared. 0 to x squared. Is that way? So it's kind of like a way to scan that region. Okay, maybe. Now watch. How would I describe this red region more directly? Which letter is going between two constants now? Y is. What's y going from to? 0 to 4. So as y goes from 0 to 4, what is x going between? So for any y, so y is going to go from 0 to 4. So for this y right there, just to pick one arbitrarily, what is x going from to? Almost. That's not x, right? That's y equals x squared. So what's the other way to talk about y equals x squared? It's x equals what? What's the other definition of the y equals x squared? X equals, if you have y equals x squared, how do you solve for x? Square root of y. That's the same stupid line, right? And yeah, weird-ass math people call curvy things lines. We do. We're crazy. So x equals the square root of y. So the red region, a way to describe that is as y goes from, get in there, 0 to 4. So now this is my floor. So really what we're doing is this. Oh. Right? My floor is now this. So x used to go between numbers and y went up to the function. Now I'm realizing that x and y are completely freaking arbitrary. Why is my coordinate system like that? Because I chose it. Can't I choose it like this? Of course I can. I can put it wherever I want to. X and y are completely arbitrary. Why are they? Just because. So as y goes from 0 to 4, x goes from 0, this is x equals 0, right? That's the y-axis, to x equals square root of y. Get out of there. Become a y. So we're so used to saying x goes between two constants, y's go between two functions. That's what we've been doing so far. But there's nothing that stops us from looking at it the other way. So let's set this integral up. Let's see what this integral looks like. So this integral is going to be d what? dy. And y is going from 0 to 4. X is going from 0 to what? That's square root of y. That's the other wall. That's the other wall it's going to. So I always imagine a little dude walking. He's walking and he's looking this way. He's like, okay, I see it. It's that far away. Now it's that far away. Now it's that far away. Every step he takes, it's square root of y, wherever the hell he is. That's how far away it is. That's the height of the rectangle that would be there. So here, the rectangles would actually be like this. If I wanted to redo all those rectangles, the rectangles would just be lying down instead of standing up. Do you like it? This is a kind of like a big shift. You guys are not used to looking at functions kind of like that way, but I want you to realize that looking at it the way we have been was completely arbitrary, to be honest. We will do a problem right after this where we have to look at it this way, just to show you that there is merit. We already know what the answer is supposed to be, right? What's the area of that red piece going to have to be? 16/3. If that does not come out to be 16/3, and as I say this, I'm like, shit, did I forget something? We're going to have to throw all this out, go home early. Let's do this integral. Let's see what we get. So let me rewrite that a little bit. Y to the 1/2 dy. What is the integral of this? Integral of y to the 1/2 is now y to the 3/2 and multiply by the reciprocal. I like it. So 2/3 y to the 3/2 from 0 to 4. Again, 0 will make it 0, so I can just forget about it. It's not going to contribute anything. When I plug a 4 in, though, how do you do 4 to the 3/2 without a calculator? What's the halves mean? Yeah, it's square root of 4. Become a 4 now, Jeff. There you go, buddy. Square root of 4 is 2. Square root is the 2, right? The bottom is on the bottom of roots. So that's the square root of 4 is 2. And then I just raise that to the 3rd power. What's 2 to the 3rd power? What is it? No. What's 2 to the 3rd power?
Oh, I was thinking
8. And 8 times 2? You get what you're supposed to get. Of course you do. Maybe. So this is funky. Do you remember when you first learned the parabolas that were this way? Do you remember the trouble you had with now everything's kind of oriented this way, the vertex is now kind of backwards and all that kind of shit? Okay, same thing. I'm not saying it's going to be immediately easy because it's not the same as what we've been doing forever, but it's not horrible. You just have to really step with it, keep your brain thinking the right way. All right, let's try one that we have to do it dy. We can't do it dx. So we got this here. Oh. So what if I had, first try to sketch that region. So chapter 6 is going to be a lot of sketching regions, a lot. So what's the natural log of 1? That's one wall I'm dealing with. The natural log of 1 is... What's the natural log of 1? You guys scare me sometimes. I feel like, would your hand pass through me if you came up here right now? What is it? Natural log of 1? 0. Okay. Natural log of 1 is 0. What's the natural log of e? 1. All right. Interaction. And the work doesn't really necessarily require this, but you should be able to graph that in there correctly. I'm not asking you to do second derivative, but what's the concavity? Am I going to connect these like this? Wah! Or like this? Wah! I gave you two sounds that sound the same. So is it going to be up or down concavity? Yeah, because the natural log goes like this, right? So it's going to look like that. Yeah, I should also put in here, just to be complete, this wall. So it's really contained. So I want that area. What would the integral look like dx? What would the integral look like dx? That's the normal way of looking at things. What would it be? Integral from what to what if it's dx? What's x doing? Going from 1 to e. And then, of course, what's the height that I'm dealing with? ln x. Mine is 0, so ln x. I like it. Is that cool? That's just your regular old integral. Do you know what the integral of ln x is? No, you do not. If you do, keep it to yourself. We don't know it yet. That takes Calc 2 to do. But what is the other way to look at this line? It's not just y equals ln x, it's x equals what? What's the y equals ln x, so x equals, how do you solve that? E to the y. How do you solve this for x? You raise both sides e. So y equals ln x and x equals e to the y both describe the same curve. Of course they do. Okay. So now if I want to set it up, now here's what I'm trying to get you guys kind of more used to. If I want to set it up dy, that means I have to have a function of y. If I want to set it up dx, I need a function of x. If I do that, shit. That's Calc 2. We're in Calc 1, Jeff. This is evil. No, turn the damn thing around. So what's it going to look like now? Integral dy. What's y going from to? 0 to 1. And then what's x going from to? Through that region, what's us going from to? From to. We could do this. Yeah, it's going from e to the y to e. Right? And which one's on top? E is. What is y? What is x going from? It's going from this wall. Well, what's that wall? E to the y. To this wall. Well, what's this wall? E. So inside is going to be the top wall minus the bottom wall. Now this freaks people out because one of those is a function of e, of y, and the other one is not. Which one of these is a constant? E. So what's the integral of e, dy? No. That's the derivative. What's the integral of 2 dy? dy. So 2y plus e. Right? You guys kind of with me? When you integrate a constant, you just throw the variable on it, because that's where it would have come from. So what's the integral of constant dy? Constant times y. And what's the integral, I'm sorry, did I say derivative? What's the integral of e? What's the integral of e to the y? What's the integral of that one? That was beautiful. What's the integral of e to the y? E to the y. Evaluated between 0 and 1. There's so many funky little things with this problem. I love it. That's e times y, and this is e to the y. So if you're not careful with how you write things, you're going to completely mess that up. So this is where I've got to be careful about 0, right? There's an e to the thing in there. I've got to actually use it. So when I plug a 1 in, what do I get? So what do I get when I plug a 1 in? E minus e. That's nice. Minus, what do I get when I plug a 0 in? 0 minus 1. E to the 0 is 1. I like it. So let me stop right there for a second. All I'm doing is throwing shit in there. I know what those are. I don't need a calculator. So this is really, really, really neat. What does this end up being? What do you get? This cancels 1. Not what I would expect. The reason I love this problem is because this is the better definition of E. I like it better. Have you guys ever heard about the compound interest definition of E? No? I don't know what kind of... When you first learned E, I hope the guy, your teacher, said something about what the shit that came from. Or else, you're like, all right, E, whatever. One way to look at it is it's the limit as n goes to infinity. Let me see if I remember this. 1 plus 1 over n to the n. I think we actually proved that earlier this semester. The more interesting way to look at it is it's the number up to which I have to integrate to make the answer 1 for this picture. So any other number I use for this wall is not going to be 1. E is the one number that makes this area 1. That's kind of a cool place for it. That's why if we did it this way, we found out, well, it makes it 1. That's a freaky number. Let's give it a symbol because it's freaky, like pi. Maybe. Okay, all right. Let me see. So there's an example of a problem. I know the last round we did was very silly in a way. It's kind of like we did all this work when we already had the answer. I totally get that, but I just was trying to show you how the method does work. Here's an example of a function. I can't choose which way to do it, because this way I don't even know how the shit to do this. So I have to do it the other way. So I want you to realize some integrals we were not able to do before once we learn this technique, we're able to do them now, maybe, if the reverse of this function is integrable. Something I can do. You guys, just like what we did here. I can integrate e to the y all day. That's like kick-ass. Can't integrate ln. Holy shit. And of course, I got people that tell me the answer to this is 1 over x, but that's silly. How do you get 1 over x? You have to take the what of ln x? Derivative. And this is asking you to integrate it. Okay, I like it, I like it, I like it, I like it. So, let's see what you guys think. Go ahead and turn this sucker over. It's the same question as what's on the front. Same idea. But now my functions are functions of y. So the first couple steps should be easy because they are just from algebra.